All right, good morning, everyone. Really quick, reminder, project part 2 is due on Friday, in case you're not aware. As requested via the evaluations, extra office hours the week of project being due, this week. What day do you want the extra office hours to be? What would be most helpful? I heard one request of Thursday. I can do whatever, that seems a little late, but we just want to do like a quick vote, not an official vote here. Tuesday. Looks like it's not going to be Tuesday. Sorry?
How many do we get? One, right? We would get one extra one then. Can we get 2 extra? I don't care. I just never go to it. What time would it be at?
We'll figure it out. I just want to figure out what day would be best for you. Because I already have all your responses in terms of what you are available. And so this is just what day would be most effective for helping you with the project. Just one additional office hour. We have office hours Monday and Tuesday this week already. So we're just going to be one day, Tuesday, Wednesday, Thursday. Okay, let's say it's going to be Wednesday. Definitely not in the afternoons. That's when all the recitations are, right? I'll look at the doodle poll and see what times are most available. So the major classes that you're taking right now are fluid mechanics, measurements, what else? Motion elements. Any other major ones? Is that it? Everything else is random from there? Okay, so I'll avoid those 3. Sure. And then after that, I can't accommodate everyone's schedule, of course, but I can do my best. Okay, it'll be Wednesday, sometime that fits within that. Okay. Any other question about the project? Yes?
Our fluids class, I think everybody takes it fluid, right? That's basically online, so we don't actually have a lecture during the fluids portion.
Okay.
Just so you know.
There's no lecture? Brave new world we're in. Okay. 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 So whatever's blocked out for fluids, don't listen to that, right? In terms of time. So just so I'm clear, you're saying if I go to the registrar, it says the time for fluids, but that doesn't apply.
Yeah. Well, there's one that starts at like 10, and then there's one that starts at 12:40 or something. So that would take up the whole like lunch period of the day, but it's sort of like an office hours instead of there's not a real lecture.
Okay. Okay, so that time is not like that, yes.
Yeah, I think that's like the only time on Wednesday.
For this class?
For fluids.
For fluids, okay. On Wednesdays.
Or it's, I don't know what everyone else is.
Okay, but some of them are on Wednesdays. Okay, that helps. Okay, so on Friday we finished up looking at these metrics. So we said that if we're going to be looking at design and control systems, it's helpful to be able to compare one design versus another one. All right, so we are trying to derive then metrics for assessing one way in which we assess a control system being the step response. So step response meaning that we have some sort of system, we put a step reference into the system, so that means if it's a robotic system, that means go from point 0 to point A. If it's a temperature in a thermal system, say going from one temperature set point to the other, it's just a change in our desired output. We're saying that for the vast majority of systems, it's going to behave like somewhat similar to a second order underdamped system, and it's going to have metrics that we can pull off the plot. And so a few of those that we looked at were rise time. We looked at peak time. Usually peak time is one that's used less often, but rise time is used often, and also settling time. In terms of time durations in which we're looking at this response. So remember, rise time can be thought of how quickly the system rises to its new steady state value. It may overshoot it, all right? So it says nothing about the overshoot, but basically how snappy the response is, how quickly it goes from the level of 0 to the next level. Settling time is the time it takes for all these transients to die out. And then also we had other metrics, one being what is C final, this is this new steady state value. And then we talked about, for this specific example, which we had a mass spring damper system with just proportional control, that our final output did not meet our desired output, right? So that would be seen as a negative thing, and we'll talk about why that is and what we can do about that in a little bit. And then the last thing that we talked about is this idea of overshoot. So overshoot is the C max minus C final, then normalized by C final. So overshoot is always given as a percentage, right? So we say overshoot, we'll say 15% overshoot, etc. Okay. So then, kind of tying everything together, these are the metrics for a step response. And then we started to look at the idea of, okay, we have the ability to change a parameter in our complete integrated system. That is proportional control. So everything else is fairly difficult to change. Usually means we're talking about swapping out pieces of hardware. But in a controller, we can start to change this proportional gain and start to understand how that influences things. So tying together pieces of the notes, if we want to understand how does proportional control affect the rise time in general, we have that this rule of thumb, this was from Friday, that the rise time is approximately equal to 1.8 over the natural frequency. And then we had an expression for the natural frequency. So we said the natural frequency was square root of k plus kp over kf. Natural frequency is in the denominator, all over m. Natural frequency in the denominator here, so we're actually going to flip the numerator and denominator. And then this would be our expression for the rise time. Okay, so if we want to make our system faster, right? So it responds more quickly, do we increase or decrease this parameter Kp? I heard increase and decrease. Who thinks it's decrease? Increase? Okay, so it's increase, right? So if we want TR to go down, right? So faster meaning the faster rise time, TR to be a smaller number. We want the denominator here to go up, right? And so this also corresponds to what we can think of as controller aggressiveness, right? So if Kp is larger, that means when we see an error, say 1 unit of error, say our error is 1 millimeter on some sort of robotic system, that means if Kp is large, that means we're giving a very large control effort for that 1 millimeter error. And if Kp is small, then we're giving a very small control effort. So the more aggressive our controller is, the more aggressive the system's going to respond. And so when we look at a response, like this one, we would see that then the response goes faster. This rise time would decrease in time. Okay, so increasing Kp decreases rise time. This is generally saw as a good thing, right? So we'll get a smiley face for this one. Yes? That's a great way to say it. Yeah. Yeah. So it sees some sort of error, right? Error is a metric of how well we're doing, and it's going to, because it's a stronger gain, it's going to react with more intensity, right? All right, so we increase Kp, rise time goes down. That's generally thought as a good thing. Our other metrics, in comparison to how rise time affects it, we said that we have Tp. So Tp equals pi over the damped natural frequency. Now this is a fairly long expression. And we'll break this out into pieces first. Remember, damped natural frequency is equal to natural frequency times the square root of 1 minus zeta squared. So then filling everything in here, sorry, this got a little difficult to read. Okay, and then if you were to simplify this, there's a lot of common terms in here. You can actually simplify this quite a bit. Okay, and so we get to something, after some simplification, we get to something that has Kp in the denominator again, right? So same reaction last one in terms of what direction an increase in Kp forces this metric. And so we're going to have that increase in Kp decreases the peak time. Again, often seen as a good thing, smiley face. Okay, so again, this is just making a more aggressive controller. C final, our expression for C final all right, so we want C final to be equal to A, right? That's what we said our reference was, the height of our reference. So as Kp increases, does C final get closer to or farther away from A? Closer, right? Okay. So you can look at this from the perspective of, say, Kp is a large number, right? So K, say it was just some normally sized number. If Kp is a really large number, then we have Kp over Kf plus Kp plus Kf. If Kp is really large in comparison to K, this term K doesn't really matter. So we get 1 over 1, right? So, but does C final ever actually equal A? Unless we make Kp infinity, right? So increasing Kp we have then C final goes to A, right? Which is good, right? So we want this. If we say we want a robotic system to go to some location, we want it to actually get there. But the caveat to this is for C final equal A, Kp must tend towards infinity, right? Okay, and that, I think you can probably imagine what happens if you have a system in which it sees just a very small amount of error and it puts infinite effort from that, right? I think you can see some disadvantages of that. All right, so there's a balance. Settling time. Okay, so for this particular design, the settling time is actually not affected by Kp. Right. We'll talk about other designs in which we can have controller gains that affect our settling time, but this one's actually no effect. So that would be the no response. All right, and then lastly, overshoot. So it's going to be a long expression. All right, so this is a long expression. It simplifies, though, into a somewhat simpler function. Still pretty complicated, though. And let me make it clear that this is all in the exponent of exponential. Okay, so this overshoot is defined by this exponential function. What we're doing is if we make Kp a larger number, that means we're making the denominator of this exponential larger, which means e to the smaller negative number, which means larger overshoot, right? So as exponential goes to really small numbers on the negative side, that approaches 1, right? And as exponential goes to really large negative numbers, that goes to 0, right? So if Kp increases, term in the exponent decreases in magnitude, approaches or goes to a higher number. So if I increase Kp, OS percent goes up, and that's seen as a negative effect. Okay, so going back to our responses here, so this is showing some sort of generic response that I just plugged into MATLAB. But if I were to increase Kp for this, we would expect that a few things would happen. The natural frequency is going to go up, right? Which means that the rise time is going to go down. So that means that when this first hits C final, it's going to be a smaller time. C final is actually going to start to approach A. Natural frequency is going to go down, so all these oscillations kind of squeeze together. And then settling time largely unaffected, but then the major deficiency of this is that the overshoot is going to go up. So this peak is going to go to a higher level. Right? Right? So this would be the case if I have a robotic positioning system, a good control system. If I'm going from point 0 to A, should kind of go and then settle off fairly rapidly at this new location. This one's going to overshoot a lot before it then settles down at this new location. So if you think of a robotic system, or many other systems, being this mass that's moving around, having wildly vibrating masses is usually a pretty bad thing for robotic systems, especially if that mass is heavy, right? That's It's a very dangerous system. It's going to make a lot of noise. It's going to cause a lot of undue wear in your system, right? So that would be a bad thing. Any questions on kind of these general responses before we get into, we'll get into some examples. We'll bring in that little, Mindy brought in that rotational system. We'll show some examples on that later on this week. Yes?
So since we can't change the settling time with just proportional control, and then like if you, anytime you increase KP, you're also increasing the overshoot. Is there basically like no point to just use only proportional control? Like why it doesn't have really get you anything at all, does it? Like you can increase your time, but then also your overshoot. So it's like
So there may be a few examples in industry where someone has used a proportional controller because basically the system has a lot of inherent damping in it already. You don't necessarily need to add damping to it. Okay, so if we look at what the settling time is composed of, this is probably the simplest expression we had of all these. Okay, so we said the settling time is equal to 8m over b, right? So b's are damping of our mass screen damper. So the system has a lot of damping in it already. Then you don't necessarily need to add other terms. So it's really a system-by-system dependent case. Okay, so now I would agree with you that you'd be hard-pressed to find very many systems in industry that do not have at least a derivative term. But we'll get into what the derivative term does later in their control system. We'll get into that. But yeah, you're right. This is just a start. This is just to get the ideas of feedback control kind of seated in all your heads. But yeah, we'll improve upon this. Okay. Any other questions on that? Okay, so then the last content I wanted to go over with is this, and this is going to be pretty helpful with your homework this week. This idea of level sets of these characteristics. Okay, so we started to define a few different characteristics, such as the decay rate, natural frequency, damp natural frequency, etc. And so and we alluded to this a little bit, but I think it's important to talk about this a little bit more in terms of level sets, in terms of how we can window out some sort of domain in terms of expected behavior. Okay. So the first off being we'll be drawing a few different versions of the complex plane over and over again. So the first thing that we said, I guess this is a few lectures back, I think probably Wednesday or so, is that we said if we have a pair of complex conjugate poles, this is representative of a second order underdamped system. This would be an example of one. So it's just the left half plane, complex conjugate poles. And we said that the natural frequency of the system is equal to the distance of these poles to the origin. So if we were to draw a vector from the origin to one of these, this would be the natural frequency of that system, this vector, the length of this vector. And so what this tells us is that any system which has poles that lie along this half circle here, I'll do my best to make this a circle. This is a level set of identical natural frequencies. Okay, so if I were to somehow, and we'll get into how you can actually do this with feedback control. If we were to somehow move the complex conjugate poles from here, from the red axis to the green axis, we would expect that our system would have the same natural frequency associated with it. So the implications of this would be TR is approximately the same for these two different systems, all right, given that their natural frequencies are the same. Okay, so we also talked about level sets and decay rate. And the decay rate is given by the real part of complex conjugate poles. So again, if we have two complex conjugate poles, the decay rate is given by the distance from the imaginary axis. So same idea, or similar arguments here. All right, so here would be our two complex conjugate poles. If we were somehow be able to move the poles as they are now here, right, the decay rate would be the same, and so we'd say that these have approximately the same settling time. Okay. We'll get into the next two in a second. Any questions on this idea, though, in terms of spaces in the complex plane? Okay. All right. So what this allows us to do, if we look at kind of a combination of these two, so just kind of combine these two ideas, I can say okay, we're going to get to this. We're not quite there yet. We're going to get to ways in which we can start to move the complex conjugate poles, or the poles around in the complex plane. And so what we can do is we can start to window out regions of the complex plane and say, let's place our poles here, not here. Okay, okay, so we can say, basically, here's where we want to place our poles. And so we come up with combinations of this. And so we can say, I want a rise time less than 0.6 seconds, and I want a settling time less than, let's use, brain's not working today. Let's do just 1 second, right? And so we can use some of these rules of thumb and these metrics trying to understand, okay, approximately where should I put my second order underdamped poles, right, if I have the ability to control that. Right, so if I say that I want the rise time less than 0.6 seconds, well, I know that the rise time is rise time, R, is approximately equal to 1.8 over the natural frequency. So that means if I want, then natural frequency is then approximately equal to 1.8 over rise time. So that means I want my natural frequency greater than 3 radians per second. Right, so what that means, if I'm starting to window out where my complex conjugate poles could potentially be, I can say, let's draw a half circle in the complex plane with radius 3, and then let's make sure my complex conjugate poles are somewhere in this region. Right. So I'm windowing out these regions here. And then similar, if I say I want settling time less than 1 second, I can say then the settling time approximately equal to 4 over sigma d, or sigma d is approximately equal to 4 over settling time. And this is a poorly contrived problem statement, so we're just going to fix this a little bit. This is made up on the fly just now. All right, so settling time less than 2 seconds. And so this would give me that sigma d should be greater than 2 radians per second. So that means what I would next draw here is at a distance 2, from the imaginary axis, I would draw this line. And I would say that I want my complex conjugate poles to the left of this. And so let me draw these all the way in. And so that means that the actual area that we're going to say is admissible is the union of these two sets, right? So it's going to be the area over here, which is to the left of this vertical line, and then we're going to go around this half circle, and then it's going to be, so basically the area to the left of both of these, right? All right, so it gives us an idea in terms of design, what types of designs are admissible and which are not admissible. And just really quick, some of you are probably still drawing this, but if you ever, we'll start using this tool called CISO tool quite often in this class. So I'll just show a quick example of this because I think some of you will find this pretty helpful for starting to visualize this. So if I say that I have some sort of generic transfer function, so I'm just making up some transfer function here. 1 over s squared plus s plus 1. And if you type in CISO tool and do then G, we'll get into the kind of the details of this when we get more into design, but I wanted to show you some of these metrics and how you can see them visually in MATLAB here. This will take a second to load up. All right, so what CISO tool is, it's a GUI. All right, it's a graphical user interface. CISO stands for single input, single output. So in this class, we're talking about only single input, single output systems. All right, and it's going to populate this with a bunch of stuff, and we'll talk about what this stuff is later. On the left is a Bode plot. Everyone should be familiar with that is. This plot right here, probably none of you have seen this yet before. This is called a root locus plot. We'll talk about what this is ad nauseum later. You'll love it. All right. But then we can start to add what are called design requirements from this. And so if you go to the root locus plot, the root locus plot is simply just the complex plane. So we have real axis, imaginary axis here. And if you right click in here and you say design requirement and you say new, all right, it gives you then all the design requirements that you can set up. So we can say, right now we just looked at settling time, right? So we said we wanted 2-second settling time. And so we went here, this would be, we want settling time to be less than 2 seconds. Okay? And so you know, now they use the opposite. So they say exclude from the yellow region and leave in the white regions. The white region is just to the left of this. So what this did is it made this exclusion zone. It says nothing to the right of -2 here. All right, if we want to add now the natural frequency requirement, say design requirements, say new. We can say natural frequency, and we said, 3, right? I believe is what we did. At least 3 radians per second. Right, and so I drew this half circle here on the plot for us. Okay, so then the region in which where we would want the poles to be would be in the white region here. All right, it's the same thing that we just did, kind of Xing out these regions, but it does it in software too. So if you ever want to check your work, you can always pull up CISO tool, just plug in a generic transfer function to get this thing up and running, but then you can start to add these and check your work. So this is relevant to a homework problem you have for this week in this tool. It also will give you, the step response here is actually not the step response of the transfer function we plugged in. We'll go through what this step response represents later, so don't be confused if this doesn't behave the same way you think the step response of the one I typed in behaves. It's more complicated than that. We'll get to that later. All right. Any question about the software tool here? Yes. Sorry? Oh, this is just MATLAB. This is MATLAB, yeah. Yes. It's in the control systems toolbox, but I believe that's a standard package with Ohio State's MATLAB package. Everyone should have it. If you don't, go talk to the people on the second floor. They'll be able to help you out with that. But it should be on all the computers on the second floor as well. I've never had a student have an issue with the computer lab upstairs having this. Okay. So that was just two of them. Let's finish out this discussion here on these metrics. Damp natural frequency corresponds to peak time. So we said that we have similar idea, real axis, imaginary axis. All right, so damp natural frequency is the distance between the real axis and that pole location. So that means that any set of complex conjugate poles that lie along this line are going to have exactly the same damp natural frequency. And so the implications are that TP, peak time, is going to be the same for, say, this set of complex conjugate poles, the ones in red, and the ones in green. And then lastly, okay, we set between the imaginary axis and a vector going from the origin to a complex conjugate pole location is given by the damping constant, zeta. So that means if we have two complex conjugate poles, their zeta value is exactly the same. That means that they are going to lie along the same vector going from the origin radiating outwards. Right? So these would be level sets of zeta. And implications. These two systems representing these complex conjugate poles would have exactly the same overshoot associated with them. Yes?
That means sigma d is zeta.
Sigma d.
Sigma d was like the distance from the vertical axis. And since zeta is 0 sine of zeta, that means the same distance.
So sigma d. Yeah, so sigma d is just so everyone's on the same page here. Sigma d is this distance from the imaginary axis, right? And so those are independent, right? So we can have the same exact zeta for the red poles and the green poles here, but they have different distances from the imaginary axis. Is that your question, or am I missing the question? where the red poles and the green poles have exactly the same zeta here. Because sigma d is the product of the natural frequency and the damping constant. So all right. Any other question about this idea of level sets? Okay, so this entire discussion has been with second-order underdamped systems, and those are nice and neat, and they have these really well-defined rules. And then here's where it all gets kind of fuzzy. Okay, is that we're going to start to look at well, I guess the reality is that there are very few systems out there that are perfectly second-order underdamped systems, right? So some may act and behave like them, but they almost always have more poles and zeros than that, right? So we're going to look at how these general rules for second-order underdamped systems are modified when we have additional poles and zeros and/or pole-zero cancellations, right? So we're usually talking about higher-order systems, all the way up to 10th order, et cetera, and trying to understand how additional poles and zeros affect their response. And so throughout this discussion for this lecture, we're going to be always comparing to our second-order underdamped system. So this would be our reference system, and we're going to look at modifications to this. Okay. So given that as the reference system, what we're going to be looking at here is if that's our our reference system, the question is what happens when we start to add an extra pole. So if we want to add a pole, that means that we have now, instead of a second order system, we have added an extra pole, and let's say we added it, say here, now we have a third order system. And when I say add an extra pole, it's not that we can just say system have an extra pole. That means that we've done something in terms of feedback control. We can actually add poles and zeros pretty easily with design of controllers. So there are ways in which we can add poles kind of as at will. But in terms of an actual system, like we can't just, unless we actually drastically reconfigure how the system behaves, it's not going to have an extra pole. But if we have a feedback control system, we can actually add poles to our feedback controller. And so we're trying to understand how this response is going to change and how we can analyze this. So this would be an example of a system with an extra real pole with it. For this next discussion, just foreshadowing what we're going to show here, we're going to demonstrate that if we add a real pole in the left half plane, the overshoot is going to increase if this real zero is less than around 4 times zeta times omega n, which is also called sigma d here. So if the pole is somewhere within 4 times, is real, and it's somewhere within 4 times this value, it's going to have some sort of effect. If it is really far out, say if I add a pole and it's way out here, it's actually going to have almost no effect at all. Okay. Very, very minimal effect to it. We're going to look at, oh, sorry, this is real zero. Sorry. Scratch the whole discussion. All right, so if we had a real zero somewhere in this region, it's going to increase the overshoot. If we add a real zero and it's in the right half plane, this may cause the system to go off in the wrong direction. We'll talk about what wrong direction means. Maybe not today. We probably won't get to that today, probably on Wednesday. If we're going to add a real pole somewhere close to the origin, it's going to increase the rise time. And the closer this gets to the imaginary axis, the larger this effect is going to be. And then, again, if we have real poles way out here, no effect, essentially. Okay. So if we add a pole to our system, it means we're taking our standard second order underdamped system, and what we're doing is we're saying we now are considering a slightly different system. We still have its nature of it being second order underdamped. But now we have an extra pole in the system. Okay, so how this is being parameterized, this is being parameterized by some sort of alpha. Okay, and it's alpha times the real part of the poles of our comparison system. So what this means, in terms of plotting this, is that we've, I think the best one's going to be going back to this original plot here. Okay, so what this means is we've added a pole, and the pole location, being real, is alpha times zeta omega n, right? So this allows us to understand behavior as we change this alpha. Right, so if alpha is 1, that means it's directly under the complex conjugate poles on the real axis. If it's 1/2, it's in between that value and the imaginary axis. If it's 4, it's just 4 times that value. So if we're now looking at C of S, which is our step response, right? So we have a step input to the system. Just like we did with the step response of a second order underdamped system, we are going to then get Ka natural frequency squared, S squared plus 2 zeta omega n, S plus omega n squared, 1 over S over alpha zeta omega n plus 1. Okay, so we're not going to actually do the inverse Laplace transform for this because it's not all that important. The main thing to point out here is that before, with this this kind of case system, we had a very well-defined response, which we could solve for, and we had basically a response we can plot out and say this is the step response. Here, it's going to be exactly the same. We're going to have unknown coefficients, of course, but then C of t is going to be equal to C1 times the step function plus C2. We'll do e to the negative sigma dt of C2 cosine plus C3 sine omega dt. These are all unknowns, plus then an extra C4 e to the alpha zeta omega n right? So this is C1. Now the coefficients have changed from a normal step response. So this was worked out on Monday and Wednesday last week. It's normal step response, and this is an additional term. Okay, so the effect of this additional term is going to be important depending on what alpha is. Okay, so if alpha is a really large number, so that means that my pole was way, way in the left half plane, this term is going to decay very quickly, right? Because it'll be e to the negative large number times t. So this is going to go away fast. If alpha is a really small number, this term, C4 e to the negative alpha zeta omega nt, this is going to persist for a long period of time, right? Because basically the way exponentials work, this is basically the alpha zeta omega n is the decay rate of this term. All right, so that's the general expression you should, or general rule you should be taking from this. So that just basically means that alpha zeta omega n much, much greater than zeta omega n, small effect, alpha zeta omega n approximately equal to zeta omega n, rise time is going to go up, and then if alpha zeta omega n is approximately equal to 0, rise time is going to go up a lot. Okay, so that would be these three cases here, right? So this would be alpha zeta, or alpha zeta omega n much, much greater than zeta omega n. That'd be this. This would be approximately equal, and this would be getting close to 0. This the rise time is going to increase a lot. So in the last minute, I want to just show this in MATLAB really quick. So we're going to have a few different comparisons. Okay, so the first is going to be, did you ever go through the ZPK way to enter in transfer functions last semester? Okay. So ZPK stands for zero pole gain, K being gain. Right? So then the syntax is quite literal then. And you guys see the help here. So we're going to pass a vector of zeros, a vector of poles, and then a gain to the system. So we're going to start off with a system with no zeros in it, and then poles at -1 plus 3i, -1 minus 3i, and then a gain of 10. And this is going to be our base system. So this is a second order underdamped system. This is what we're going to compare everything to. So if I plot this, then I can plot the step response and this is the step response. So nothing too informative or interesting here. Standard step response. Now I can compare this to a system in which I've added a pole to it, and I've added this pole at -10. So far away from the real part of my complex conjugate pole. So here's my transfer function with added poles to it. I can now plot this. Okay, and so we should expect almost no effect, right? And so if we look at these, the blue line was the original plot, red line is the next plot. Pretty similar, right? Very, very minimal effect by putting a pole way in the left half plane. Yes? Yeah, so that has to do with the way that ZPK works. All right, so I wanted to have, I've added a pole at 10, right? So it's written as S plus 10, but I also wanted the steady state value to be the same to compare better. All right, so if I would have not done that, it would have been 1/10 the height. All right, so that's just for visualization. Okay, second comparison. This is adding a pole at 1. Okay, so this should have decreased the rise time, which you see. So this is a considerable effect to the rise time. Sorry, that cyan line is probably not showing up too well way in the back there. And then last point of comparison is putting a pole really close to the origin at 0.1. Oops. Oh, I just overwrote that. All right, and this now should have a really long rise time. So this so if you notice, this were all our previous plots. They now look small in terms of the time scale, and so this is now the response of the system. Okay, so as this pole gets really close to the origin, it's no longer acting like a second order damp system, so those modes are still in there, that they're just so small in the magnitude of their coefficients that they become insignificant. So what is dominating the response is that pole really close to the origin. So we'll talk a lot about how, if you have higher order systems, what poles dominate the response. This is the case of, basically, it's always going to be the case that the pole closest to the origin is going to be the most dominant. We have a pole really close to the origin, it acts like a single real pole as opposed to a second order underdamped system, even though if you were to write out the inverse Laplace transform, you would still have those cosine, even the negative sigma dt cosine sine terms in there. But you can only really see the real pole. Yes? Exactly. The additional pole is dominating this response. Yeah. It's no longer acting like a second order underdamped system. Okay. Whew, I went way over today. All right. See you on Wednesday.